What's up guys? In this video, we'll continue the development of the client-side deep learning application we started last time. So let's get to it. In the last video, we built the UI for our image classification web app. Now we'll focus on the JavaScript that handles all the logic for this app. We'll also start getting acquainted with the TensorFlow.js API. Without further ado, let's get right into the code. Recall in the last video we created this predict.js file within the static directory but left it empty. This file now contains the JavaScript logic that handles what will happen when a user submits an image to the application. So let's look at the specifics for what's going on with this code. We first specify what should happen when an image file is selected with the image selector. When a new image is selected, the change event will be triggered on the image selector. And when this happens, we first create this file reader object called reader to allow the web app to read the contents of the selected file. We then set the onload handler for reader, which will be triggered when reader successfully reads the contents of a file. When this happens, we first initialize the data URL variable as reader.result, which will contain the image data as a URL that represents the file's data as a base64 encoded string. We then set the source attribute of the selected image to the value of data URL. Lastly, within the onload handler, we need to get rid of any previous predictions that were being displayed for previous images, and we do this by calling empty on the prediction list element. Next, we get the selected file from the image selector and load the image by calling read as data URL on reader and passing in the selected image file. We then instantiate this model variable, and we're going to define it directly below. Now, this below section may look a little freaky if you're not already a JavaScript whiz, so let's see what the deal is. Here we have what's called an IIFE, or immediately invoked function expression. An IIFE is a function that runs as soon as it's defined. We can see this is structured by placing the function within parentheses and then specifying the call to the function with these parentheses that immediately follow. Within this function, we load the model by calling the TensorFlow.js function tf.loadModel, which accepts a string containing the URL to the model.json file. Recall from the last video, we showed how the model.json file and corresponding weight files should be organized within our static directory that's being served by Express. We're first going to be working with VGG16 as our model, so I've specified the URL to where the model.json file for VGG16 resides. Now, tf.loadModel returns a promise, meaning that this function promises to return the model at some point in the future. This await keyword pauses the execution of this wrapping function until the promise is resolved and the model is loaded. This is why we use the async keyword when defining this function, because if we want to use the await keyword, then it has to be contained within an async function. Now, in the time since the last video, I've added a progress bar to the UI to indicate to the user when the model is loading. As soon as the promise is resolved, we're then hiding the progress bar from the UI, which indicates the model is loaded. Before moving on, let's quickly jump over to the HTML we developed last time so I can show you where I inserted this progress bar. So here we are in predictwithtf.js.html, and you can see that right within this first div, the container, I've inserted this row where the progress bar is embedded. We'll see it in action within the UI at the end of this video. Alright, jumping back over to the JavaScript, we now need to write the logic for what happens when the predict button is clicked. When a user clicks the predict button, we first get the image from the selected image element. Then we need to transform the image into a rank 4 tensor object of floats with height and width dimensions of 224 by 224, since that's what the model expects. To do this, we create a tensor object from the image by calling the TensorFlow.js function tf.fromPixels and passing our image to it. We then resize the image to 224 by 224, cast the tensor's type to float32, and expand the tensor's dimensions to be of rank 4. We're doing all of this because the model expects the image data to be organized in this way. And note that all of these transformations are occurring with calls to functions from the TensorFlow.js API. Alright, we have the tensor object of image data that the model expects. Now, VGG16 actually wants the image data to be further preprocessed in a specific way beyond the basics we just completed. There are transformations to the underlying pixel data that need to happen for this preprocessing that VGG16 wants. In other libraries like Keras, preprocessing functions for specific models are included in the API. Currently though, TensorFlow.js does not have these preprocessing functions included, so we need to build them ourselves. We're going to build a preprocessing function in the next video to handle this. So for right now, what we'll do is pass in the image data contained in our tensor object as is to the model. The model will still accept the data as input, it just won't do a great job with its predictions since the data hasn't been processed in the same way as the images that VGG16 was originally trained on. So we'll go ahead and get this app functional now, and then we'll circle back around to handle the pre-processing in the next video and insert it appropriately then. Alright, so a user clicks the predict button, we transform the image data into a tensor, and now we can pass the image to the model to get a prediction. We do that by calling predict on the model and passing our tensor to it. Predict returns a tensor of the output predictions for the given input. We then call data on the predictions tensor, which asynchronously loads the values from the tensor and returns a promise of a typed array after the computation completes. Notice the await and async keywords here that we discussed earlier. So this predictions array is going to be made up of 1,000 elements, each of which corresponds to the prediction probability for an individual ImageNet class. Each index in the array maps to a specific ImageNet class. Now, we want to get the top 5 highest predictions out of all of these since that's what we'll be displaying in the UI. We'll store these top 5 predictions in this top 5 variable.
Top 5, top 5, top 5.
Before we sort and slice the array to get the top 5, we need to map the prediction values to their corresponding ImageNet classes. For each prediction in the array, we return a JavaScript object that contains the probability and the ImageNet class name. Notice how we use the index of each prediction to obtain the class name from the ImageNet classes array that we imported from the ImageNet classes JavaScript file. We then sort the list of JavaScript objects by prediction probability in descending order and obtain the first 5 from the sorted list using the slice function. Lastly, we iterate over the top 5 predictions and store the class names and corresponding prediction probabilities in the prediction list of our UI. And that's it. Let's now start up our Express server and browse to our app. Alright, we're here and we've got indication that our model is loading. So I paused the video while this model was continuing to load and it ended up taking about 40 seconds to complete. Not great. It may even take longer for you depending on your specific computing resources. Remember though, I said we'd run into some less than ideal situations with running such a large model like VGG16 in the browser.
I warned you, now you will pay!
So the time it takes to load the model is the first issue. We've got over 500 megabytes of files to load into the browser for this model, hence the long loading time. Alright, well our model is loaded, so let's choose an image and predict on it. About a 5-second wait time to get a prediction on a single image. Again, not great. Oh, and yeah, the displayed prediction isn't accurate, but that doesn't have anything to do with the model size or anything like that. It's just because we didn't include the pre-processing for VGG16, remember? We're going to handle that in the next video. There, we'll get further exposure to the TensorFlow.js API by exploring the tensor operations we'll need to work with to do the pre-processing. Alright, so we've got that coming up, and then afterwards we'll solve all these latency issues attributed to using a large model by substituting MobileNet in for VGG16. Let me know in the comments if you were able to get your app up and running, and I'll see you in the next video.